Welcome everybody to today's talk within the Design++ speaker series provided to you by Design++ initiative of the ETH in Zurich. My name is Michael Kraus and I'm happy to be your host today. It is also my special pleasure to welcome our guest and lecturer of today, Professor Katrin de Wolf. And before I introduce you to our speaker and her talk, let me shortly provide some background information. The Design Speakers series is a recurring event where we will provide some information and invitations to upcoming events in due time via our mailing list, the homepage, and our YouTube channel. You can find all updates on the dates, speakers, and topics of this spring on our homepage. And if you want, you can also automatically subscribe to our calendar. You're warmly invited to have a look at the previous presentations which are hosted on our YouTube channel. The link of that can be found here. At the moment, there is a number of professors from architecture, civil engineering, and computer sciences from ETH in Zurich involved in the Design++ initiative. For the running business, there is a team of 3 leading postdocs responsible for operating our immersive design lab, together with the research and teaching activities. A growing number of scientists and chairs and professorships is associated to us. So in case you're interested in the future of connecting AI, machine learning, and extended reality with the AEC, just reach out to us. We are more than happy to discuss any further ideas and projects with you. Having said all that on the background of Design++ and the speaker series, now let me finally introduce to you the speaker of today, Professor Katrin de Wolf from ETH in Zurich. Katrin is Assistant Professor of Circular Engineering for Architecture at ETH and conducts research on digital innovation towards a circular built environment. She is the Director of the Chair of Circular Engineering for Architecture, which is an interdisciplinary team of civil engineers, environmental engineers, architects, anthropologists, urbanists, and computer scientists who collaborate towards automating the reuse of building materials. A key element in Katrin's work is ensuring a continuous link between academia and industry. Therefore, she works with real-world examples, such as the Centre Pompidou in Paris. After studying civil engineering and architecture in Brussels, she obtained a PhD in building technology at the MIT. She also worked at the University of Cambridge, École, polytechnique, fédérale de Lausanne, and the University of Technology Delft, as well as in design firms such as Arup, Ney Partners, and Elioth. The talk of today, which has the title Digitalization for Circularity, will illustrate how we can automate the matchmaking of reused building materials and new projects through digitization for circularity. Exploring how we can adopt digital technologies in the AEC industry, the research here analyzes how we can shift towards a circular paradigm. Buildings are complex, multivariate problems addressed by numerous stakeholders. Automating reuse of materials in architecture can fill this gap by connecting actors across the value chain. The work with digital innovations that have been applied in other sectors, like artificial intelligence algorithms in social media, robotic manufacturing in the current aerospace industry, or blockchain technology in financing, can augment the skills of AEC players towards connecting the end of life of one building with the state of the art of another. So please have a look at Katrin's papers and her homepage, which I put here. And yeah, all that background information is also provided on our YouTube channel or our homepage. And yeah, now no further words from my side. I would hand over to you, Katrin.
So thanks for inviting me. I'm very happy to be here online with all of you and to talk a bit about the work that the Circular Engineering for Architecture Lab, or CEA Lab, is doing on digitalization for circularity. And some of you might already know a bit about the work that we did on a project that we built that was testing different digital innovations from other sectors and bringing it to the construction sector for enabling a circular economy in the built environment. Now, as Michael mentioned, I worked, for example, with the company that was renovating the Centre Pompidou in Paris, and specifically this facade that you see here with this bent glass on the hallways and the escalators of this facade. It's called the caterpillar of the Centre Pompidou. And because of the renovation, we needed to replace the glass due to changing security norms. And so we're looking for a new home for the glass. And to do that, here is the new home for the glass. We were able to find a young designer firm called Maximum, thanks also to the collaboration of Pavillon de l'Arsenal in Paris, and all different actors who were involved in trying to find a new home for the glass, which is not such an easy thing to do today, to reuse building materials. It's not so straightforward, even though it should be. All right, so why do I care so much about the reuse of these building materials, such as the glass from the Centre Pompidou? Well, first of all, the building sector is responsible for about 39% of all of our greenhouse gas emissions. So as actors of the construction sector, we have a huge role to play in the climate crisis. But it's not just about the greenhouse gas emissions, it's also about much more than that. And often when we talk about greenhouse gas emissions, we talk about the operational emissions to heating, cooling, ventilation, lighting, and so on. But when you look at the full life cycle of a building, it goes from the extraction of the raw materials to the transport of those materials to sites, to the construction, maintenance, and then in the end, end of life, demolition often. And so when you look at this full life cycle and you think about all of the resources that we deplete also to build our buildings, it's really crazy. For example, we mine about 40 billion tons of sand every year, just because desert sand is too fine for construction to make concrete, for example. And this mining of sand is often to the cost of biodiversity, and we even have sand mafias creating, because sometimes it's done illegally as well. Just because we need so much of it for construction. We also create a lot of waste. Here you see the Kingdom in Seattle that was demolished only 26 years after its construction. And this happens so much. Our buildings have increasingly shorter lifespans. And this is really a problem that we create this huge amount of waste. In Europe, for example, 30% of all of our waste comes from the construction and demolition sector. And this number is even higher in Switzerland. Now, why is that? Well, it's because our construction sector is really built based on a linear model, a linear economy model. We extract raw materials, we produce building materials, we use them, and then we dispose of them. This is a picture I took in Zurich. These are the typical demolition sites. Anywhere you can see, we just demolish things, and yeah, this is not how it's supposed to be. Now, often we talk about recycling, and our lab is really working on reuse. And I just want to pause a bit on the difference between recycling and reuse. So when we think about recycling, it's using energy to bring a component back to its raw material. So think of wood chips, for example, or melted steel, or crushed concrete aggregates, and so on. When we talk about reuse, it's actually keeping the component as it is and trying to reuse it. Sometimes it has a different function, but it's still the component, and all of the energy and effort that went into making this component is saved as well. So think of wooden window frames that were used for the European Council in Brussels, or think of steel beams that you can reuse, or concrete slabs that you can reuse. This has been done before. But it's not the business as usual in the construction industry right now. And that's really what we're trying to see, whether we can explore digital innovations that can make this business as usual. And here's why it's important to think about reuse and not just recycling. It's when you look at this structure here, this is the Maison du Peuple, designed by Victor Horta, who is a famous Art Nouveau architect in Belgium. And this building was disassembled in 1965. And then they stored the structure for about 35 years until they found a new home for the structure, which is what you see here, which is the Hortazaal in Antwerp. Now, my PhD students went there last week to scan the structure, to also make a point cloud of the structure and try to evaluate how much embodied carbon was saved by reusing a structure and comparing it to similar spans of other buildings. But what I wanted to show with this example is that it would be a shame to have melted down the structure back to its raw material. If we would have recycled it, that's what we would have done. But we would have lost all of the effort, all of the art, all of the craftsmanship that went into making this structure as well. And of course, all of the labor. And so that's also something to take into account. Of course, you're probably thinking, well, they stored it for 35 years. That's not a very efficient way of dealing with the construction waste, and that's totally right. We should not store materials for 35 years. We don't have capacity, we don't have space for that. And that's why we need to align the moment when we disassemble a building like the Centre Pompidou that you just saw here in this video, and the moment when we reuse those materials in a new construction site. So here, the glass was immediately reused in the new project that I showed you a couple slides ago. But to do so, we really need to align the moment of the end of life of one building with the start of life of another building. And that's sometimes tricky to do. We need a lot of help also with logistics. And that's really where our lab's research comes into play. It's really trying to use digital innovations to have as much information in advance as possible and to start trying to do the matchmaking of who needs materials and who has materials available for reuse. Now we do this in 5 different steps. So first we collect data on a city scale to see where and when materials will become available for reuse. Second, once we've established a building that will be demolished, we try to detect which materials are in there. Then we disassemble the building and try to make this as efficient as possible. Then we create techniques to distribute them as efficiently as possible. And in the end, we also change completely the way we design buildings. We shift this around. Now, could digital innovations help us with these different steps? Could digital innovations help us not only reuse this glass that you saw from the Centre Pompidou, but also the materials of other buildings, not just glass, but all building materials, and not just the Centre Pompidou and iconic buildings like the Centre Pompidou or the Maison du Peuple from Victor Horta, but also of all other buildings worldwide. And that's really what we want to try to solve this question. How do we reuse as much as possible in the construction sector? And to do so, we really need digital innovations. We strongly believe that that is really the way forward as one of the techniques to help us to go forward. And when you look at the construction sector, it's quite slow in adopting innovation. And very much digital innovation is quite slow. The adoption of digital innovation is quite slow in the construction sector compared to other sectors. For example, in the financial sector, 20% of traditional banks already use blockchain technology. The car manufacturing industry is full of robotic fabrication. Artificial intelligence is literally everywhere, from online marketplaces like Amazon to matchmaking platforms such as Tinder. And so would all of these digital innovations also be useful for the construction sector? And that's really the question we're trying to answer. And we're trying to look at things from digital fabrication to blockchain technology, going through different aspects like computational design and artificial intelligence, to see where it could be useful to adapt those new technologies in the construction sector and to solve the question of how to shift from a linear to a circular paradigm. All right, so of course, when we do this research, theoretically things are always possible, but then in practice, we have some real world challenges to deal with. And that's why we also apply it to real world case studies. And here is an old car warehouse in Geneva that we actually disassembled. We did this in collaboration with Materium, who is one of the big reuse actors in Geneva. And they had access to this demolition site. So this building was getting demolished, and we went there and assessed all of the materials that we could recover, and then actually disassembled the building and built a dome with the recovered materials. For those of you who joined earlier, we were talking about this dome and where it would be, there will be a version of this dome on campus this summer. All right, so as I mentioned, there are 5 steps, and the first step is really about data. And And it's really important to have as much data as possible to predict when materials will become available for reuse in a city. And during my PhD at MIT, I already started to create a database called the Database of Embodied Quantity Outputs, which was collecting structural material quantities of buildings from companies such as Arup or Thornton Tomasetti. And it was giving graphs like this, where you see structural material quantities in kilograms of material per square meter of floor area. And then on the x-axis, you see the number of stories, for example, but you could also see the type of building, the function of the building, the year of construction. You can see different type of characteristics so that you can see a bit what consumes a lot of materials, what has a lot of global warming potential, because this database was also used to compute the embodied carbon of these buildings. Now, what's interesting about this graph, why am I showing this graph? Because I think it's funny that it's confirming what Fazl Khan was already saying in the 80s, that when you build over a number of floors, you're paying a premium for height, because there's not just the normal loads to take into account, but other things like the wind loads and so on. And so you have more material per square meter of floor area for a tall building. Another thing that I learned from this database was that the Beijing Olympic Stadium was had more than 10 times the embodied carbon per seat than the London Olympic Stadium. And that's interesting also because when you look at the design goals of the two different Olympic Games, London Olympic Stadium was built 4 years later, and a lot of things had shifted in what the priorities were in those 4 years. Sustainability became really more part of the conversation of the designers, and they had put this as a main goal at the beginning of their design stage. So they used lower carbon concretes, they reused some of materials from a gas line construction site nearby. They designed it for partial disassembly after the games to downsize also the stadium and so on. So it is possible for designers to have a huge impact on the climate consequences of their designs. Now, this database led to the Structural 2050 commitment, SC 2050, which was created together with the Carbon Leadership Forum and the Structural Engineering Institute. And this is really gathering structural engineers to join the movement, to share information about their structures, and then lower the embodied carbon of their structures each year. Now, when I was at EPFL, we also upscaled this to a city scale during my postdoc at the Structural Exploration Lab, where we looked at Geneva throughout time, from 1850 till today. So we have an evolution of the embodied carbon emissions from that date till today. And this really learns a lot about the past construction and demolition sites. Now, we don't only look at the past. At the CEA lab at ETH Zurich, we now also look at the future. We try to predict the future, and we use AI and more specifically machine learning to do that, to predict which building materials will become available for reuse in the future. So we apply big data analytics on various data sources and detect demolition and renovation projects. And algorithms can identify the patterns in the data so that we can make those predictions. And for example, here, the image that you see is that we have developed machine learning techniques for detecting windows available for reuse from Google Street View images, as you can see here. So this is the work of Deepika Raghu. She labeled the Google Street View images using an online annotator to train the model. We explored instant segmentation techniques to identify reusable components, and we used a masked region-based convolutional neural network framework for computer vision tasks for detecting the objects such as windows from images of the facades. Now, there are many data sources available for this machine learning work, and in different cities, we have a lot of data from Google Street View images, as you see here for the city of Zurich. This is available for most cities worldwide, so it's a really cool data source. We combine this then with cadastral GIS data, geographical information system data. This is for the city of Zurich. We were able to draw a map from residential and non-residential buildings or from different construction periods. So here you see, for example, the green is from 1800s, the orange from 1900, and so on. Here is also just for residential buildings, those construction periods. So you see, we can do a lot with this cadastral data already. Of course, we have other data sources. We can use social media images, that people post more and more about their buildings online. We can also use public record data. In Zurich, we're quite lucky because there's a lot of public record data on the city of Zurich that we can see here. You can see a few examples here. What's also very interesting, especially when you try to predict the future, is collaborate with insurance company data, with insurance companies to get some of their data, because they also try to predict the future and when they invest as well. This is a project done by my colleagues from the Computer Vision Lab. It's called the Varsity Project. They basically made a 3D model out of Zurich based on aerial photos, on street side photos, public webcams, social media, and so on. So that's a really cool project. Was funded by the ERC, and I would really recommend you to take a look at it. For our work, we also use historic photographs. Here are pictures of the city of Zurich that were made by a photographer in the 20th century. So we have also the exact addresses of all of those buildings, which enables us to also see whether those buildings still exist and how they've evolved over time. That's always very interesting to learn from the past to predict the future. We also try to use image classification to define which structural elements can be reused based on images of the structures, which are corroded or not, damaged or not, distorted or not, bolted or welded, and so on. And we then tailor reuse and recycling strategies to prevent waste as much as possible. So machine learning and computer vision show really promising potential to visually collect data on building specific characteristics relevant for component reuse. All right, this brings us to the second topic that we address in our lab, the detection of building materials in a building before we demolish it. So we use several digital technologies in the field of reality capture. We use simple phone or camera images, or images from autonomous devices such as drones. We also use cameras on top of our hard hats that remember our walking path in the building in order to locate where we took the photos from or the videos from. Here we see Brandon Byers, one of my PhD students, who is using the OpenSpace.ai equipment to do so. And he's walking around in the building in Geneva that we then disassembled. Then we use photogrammetry to process the images into estimated point clouds of the buildings. This is the work of another researcher in my lab called Matt Gordon. So these images show the point clouds that we made of the old car warehouse that we disassembled in Geneva. And so this building was belonging to Fiat, Lancia, Alfa Romeo importers in Switzerland, but is now obsolete, so they are demolishing it. And so we get to use those buildings to train our recognition software and detection software. And of course, then we try to salvage as much materials as we can as a research lab to build our structures with. So we also test methods such as light detection and ranging, or LiDAR scanning. We tested full-scale LiDAR scanners, which have really the highest accuracy in collaboration with Design++. This is equipment that we got from the Centre for Augmented Computational Design in Architecture, Engineering and Construction and Design++. So here you see a video of Matt Gordon, who is using the LiDAR scanner in the DFAP house, which many of you know, in the Nest building at EMBA. And what was very interesting about this research was that we could compare it really with very accurate data, because it's digitally fabricated. So we know exactly everything that's in this building to a precision. And so we can compare our point cloud results to reality quite well. So this was the results of that work. Now, we also want to explore more portable versions of LiDAR scanning and so on. And I'll show you later also some results of the phone camera images that we did. Here you also see the Huber pavilions, for those of you who know the Hungerberg campus at ETH. These are pavilions that were built for the architecture students quite a few years ago and that are about to be disassembled this year. And so we try to capture also this building before it gets disassembled. This is really the aim of our work, is pre-demolition, going to get as much information as possible about the materials in there. This is me with my my phone trying to use the LiDAR capabilities on the phone. Some smartphones have LiDAR capabilities, and then you can use some apps that have been developed by some of our colleagues in ETH and EPFL that use this to have a more accurate vision. But of course, it's not as accurate as the full-scale LiDAR scanner that you saw earlier. But the idea here is to understand how we can use affordable and mobile methods as well in on construction sites, because we cannot expect everyone, of course, to buy 80,000 francs worth of equipment. All right, so here is a point cloud that we made out of one of the parts of the structures in Geneva. And of course, once we have a point cloud, we also need to shift it towards a BIM model, because this is a lot of data points, but what we really need is a BIM model or an inventory of the materials. And so to do so, we create BIM models using statistics, using point density, using prediction models to do so. So here you see a bit where we try to detect where the columns and the wall and the beams are and so on to create this BIM model. Now, next step in our research, what we really would like to explore is collaborating with the Robotic Systems Lab here at ETH Zurich. And they have done some work with their robot called Animal, which is carrying one of those portable LiDAR scanners that I showed you earlier, and that is making a digital twin of the campus. And this could really help us make a very autonomous method of making this inventory of materials in a building before it gets demolished. All right. So once we have the geometry, of course, of the building, we also need to know what type of materials there are in the building and in what condition they are. And to do so, we use computer vision techniques. This is still the work of Matt Gordon, where he detects which materials are steel, masonry, concrete, and so on. And so those computer vision techniques can also be used to look at the condition of the materials in advance. So this enables us to create a building material inventory where we have for each of the materials that we want to disassemble, the type of wood, for example, the dimensions of these beams, the condition, the quality and of the surface of the beams, and so on. So here is the BIM model and the inventory that we created of the building in Geneva. And this inventory was very useful for then the design stage, which I'll talk about later on. One other thing that we are planning to explore with the Design++ community is how to use virtual reality also to walk through a building pre-demolition and having information about the building right away through virtual reality. All right, so once we have as much information as we can get from the building, we have to start a disassembly of these obsolete buildings. And to do so, we also explored different techniques, but what we really do is just actually disassembling the building in Geneva. Here is a picture of another building in Bern that we disassembled with students from EPFL when I was teaching there, together with Martin Fröhlich from the East Lab, and with Renaud Harlingen from Rotor. And this was a building that was about to be demolished by Losinger Marazzi to make space for real estate. And it was the old tram depot in Bern. And it was dating from 1906, so we didn't have much information about the building other than these blueprints, which we found in a very random way when some guy walked by the construction site, or the demolition site, or deconstruction site, I should say, and told us that he had those blueprints at home. So some private person had the information of the tram depot. So in the meantime, as you saw on those images, my students were exploring how to disassemble such a structure for reuse. This is me cutting a steel beam in the Geneva warehouse that I talked about. And this is a very interesting way of learning about the deconstruction of buildings and the energy that this costs, because we had to recharge our batteries of those battery power tools every every beam that we were cutting. So it taught us a lot about the energy needed for cutting those beams. So I think this also makes us think about those connections in the buildings. The welded connections are obviously a bit more energy consuming to disassemble than bolted connections, for example. This is us sitting on our beam. We were trying to reproduce this picture, but of course we were not sitting as high as these iron workers in New York. So this is me trying to, or actually disassembling a pipe that also in this building before it got demolished. And you'll see later on what we did with this pipe. Here are some OSB plates also that my PhD students are disassembling. This is worked a lot now with some of the shortage and distribution problems. And here you see us disassembling those timber beams, which are much easier to disassemble because they were just screwed together. And then came the challenge of transporting those beams, because those beams are quite long. Some of them were 7 meters long. And this is Brandon Byers who is carrying those beams. And this is me and Deepika Raghu who are carrying some of the beams to the van. And this is our van, which was only 3.5 meters long. So of course, there is a challenge there to bring them to campus. So we had to associate with materials transporters so that we could bring the rest of the beams. And then we had to store them also on site in at ETH, where there is also not so much space, of course. We're a campus, we're not meant to store building materials. So there's also a challenge there. So this was really hands-on learning also for the entire team, that we need a better logistics system for deconstructing, transporting, and storing materials, and while we process them for reuse in a new building. So here you see our processing. We were scanning the beams to see whether we had forgotten any screws or metals in the timber beams. So see here, and then we remove them. And then we plane also the beams to remove any surplus. Then we explored also how we could use digital fabrication to assemble the dome. But in the end, we used only digital fabrication for the connections, because of course, sometimes you really have to evaluate when it's useful to use robots and when it makes sense. However, I think it's interesting to talk about Zen Robotics, who are using computer vision as well, and robots to sort construction wastes. So as you can see here, they are sorting construction waste so that they can recycle it afterwards. So here you see they take pieces of wood, I think, into one bench and then stones in another and so on. So I think it's not so far-fetched to think about robotic fabrication being used for the reuse in the future, not just for recycling. All right, so once we have disassembled the building, we needed to think about a smart way to distribute those elements in the future. And what we did is we used QR codes to label each of these beams. And this is the work of my PhD student, Brandon Byers, who engraved all of those elements with a laser engraver. And he was also testing, also making labels and so on. Also, you can really go from different directions, but here we chose the QR codes. And when you scan the QR codes, it brings you to a database that you see here. That gives you all of the elements of the dome that we constructed and where those elements had been before, and what the dimensions are, what the weight is, what the condition of the materials is, the type of wood, and so on. It gives a lot of information. It also gives you information about all of the other components of that same type, and also all of the different types of components that you have in the dome. So this is what we call a material passport of a building. You have an information on each of the materials, and you know exactly how much of those materials are in the building. And this is something that we work on together with companies such as Madaster or Concular. We try to see how they bring this type of thinking to the market. Having a material passport of your building, how can this help you earn more out of your building as a building owner? It's not just about the value of your building as a rentable space, but also the value of the materials that are in your building. And once you disassemble or renovate your building, what can you get for these materials, and how can we reuse them and upgrade or upcycle them as much as possible? All right, so to label these, we use QR codes, as I mentioned, but you can use anything from barcodes to RFID chips. The advantage, for example, of RFID chips is that it doesn't automatically need to be visual to be scanned, but then you need a special scanner. We chose the QR codes for the dome just because we wanted everyone with a smartphone to be able to read the information when they walked by on our site. But there are many interesting different ways of labeling materials, and we wrote a conference paper about this recently, if you're interested. All right, so once you have things to label and link something with the material passport, with a digital twin, then you can also connect different buildings to each other and start using the Internet of Things as well to basically connect information to each other and help with renovation, with replacement, with refurbishment, and so on. So that's also very useful to explore. And as I showed earlier, we also do research on a city scale with the data on the city of Zurich. So this is combining these two research streams. Now, the construction industry has regularly been cited as one of the most fragmented sectors, and blockchain technology could help connect the supply chain through transparency and traceability for the relevant parties. So blockchain technology could give transparency into where materials are, but also traceability, showing where materials have been. And Tata Steel is, for example, using blockchain to track things like CO2 emissions or product conditions or change of ownership for steel beams, from raw materials to use to the reuse or recycling of those beams. And every beam is tracked through a unique ID or material passport registered in a blockchain system. We have a postdoc starting soon, Melia Honig, who is going to explore also the potential of blockchain technology for circularity in collaboration with the Future Cities Lab. All right, so with the tracking and tracing identifiers like barcodes, QR codes, and chips, and the linking to their digital twin, we can also try to explore what is possible to follow them throughout their life cycle. We can also trade them or match them. With the help of AI, we can create a matchmaking service for the construction sector, basically a Tinder for reused building elements. Companies such as Access Materials Exchange Platform, EME, have already started using blockchain, AI, and so on to do so. All right, so last but not least, our last step is the design. Normally, this is the first step in the conventional way of designing buildings, but for us, it's the last step. Once we have looked at the end of life of one building, made the inventory of it, have labeled them so that we can track them in the future and so on, disassemble the building, when we can start designing the new building with this available stock of materials. Now, together with MIT, we have applied computational design algorithms to a stock of timber elements in order to create geodesic domes, as you can see here from this image. So here it was for a timber framed house in the US. But here you see the inventory from our building in Geneva. And so we did exactly the same to build the dome on the right that you see here that will be built on, that was built on the ETH campus this winter. And that is now standing in Ghent. So we discussed the different choices that you can parameter into Rhino and Grasshopper, and we discussed the different design choices that we put in the computational design algorithm in order to make the best choice for our dome. So we wanted to use the shortest beam first in order to keep the longest beam for a bigger construction later on. We also wanted to minimize the waste, of course, which is the white part that you see here with the dotted lines, which we then also used to build furniture for our dome. Now here you see the connections that we used, and I made them from pipes, those pipes that you saw earlier that I was disassembling in Geneva. And that's why I said this is not a pipe, it's a connector. This is referring to this Belgian artist that says this is not a pipe, that is questioning our view of the world. And we also want to question your view of building materials to see that one building material can be used for something one day, but then instead of becoming waste, it could be used in another way the next day. So our pipe was, of course, not designed to be a connector, so we had to adapt it. And to do so, we used digital fabrication. So while part of the team was assembling the dome, the other part was cutting round shapes into the OSB boards that we had left, that you saw earlier as well, using computer numerical control or CNC cutting or milling to adapt really what we had to the reused materials that we found, the pipes, to strengthen it, to aesthetically finish them, and so on. So it's really showing that a pipe can become a connector, like a caterpillar can become a butterfly. So I'm happy to say that our dome has been used at ETH for eating and gathering and so on. Then has been put at the University of Ghent, where it has been used as a TV and radio station for talks that were live streamed on circularity and other topics. And it has many new homes ahead, such as an outside meeting space for a city hall or a greenhouse. So many different functions will it will have many different lives in the future. So I'd like to conclude with this quote from Buckminster Fuller: "You never change things by fighting the existing reality. To change something, build a new model that makes the existing model obsolete." And I think we clearly need to change from the current linear model to the circular model that I talked about, because we're depleting resources, we're polluting, we are generating waste for our construction industry. But if we really want to change this, we need to show that the circular model is competitive enough, is more efficient, is cheaper, is faster, and it's just the most common sense thing to do. And I strongly believe that we need to explore digital innovations in order to help us get us there. And that is what the Circular Engineering for Architecture Lab is all about. So if you want to learn more about our work, you can scan this QR code, and this will bring you to the link of our website, but also our social media links. So feel free to scan it and learn more about the research of the wonderful, talented researchers that we have in the lab. And here you see also a picture of all of, well, not all, everyone was there that day when we took the picture, but it's a part of the CEA lab here. Thank you very much.
Thank you, Catherine, for this interesting talk and the discussion. Your time and efforts are very much appreciated. As I said before, I will upload the information of this talk together with the video to our YouTube homepage. Eventually, I want to highlight our next talk on the topic of conceptual design of structures at the interface between human and machine intelligence, which is delivered by Professor Pierluigi D'Acunto on the 26th of April at 4 p.m. So roughly 2 weeks. So yeah, finally, thanks again. Stay safe and see you soon.